In this video, we study Taylor and Maclaurin series. The Taylor series is a special power series that can give us a power series expansion for functions that cannot be presented as power series. For example, sine of x. It's not easy to write it as a power series directly. Cosine, e to the x, and many functions cannot be presented as power series directly, so we need to we can present them as power series by using Taylor series. Maclaurin series is a special case of Taylor series, as we will see in this lecture. Now, one reason that Taylor series are important is that they enable us to integrate functions that we couldn't integrate using the techniques that we learned in calculus. Previously in this course. For example, integration by parts, integration by substitution, or direct integration, or partial fractions. So all these techniques cannot solve a problem like this: integral of e to the x dx e to the x squared, or e to negative x squared dx. We can't integrate this using the integration techniques that we learned. So we can now, by using Taylor and Maclaurin series, we can approximate this integration. So, and there are many applications for this type of series. So let's start with the formula for Taylor series. The formula for Taylor series is the following. Taylor series can be given by, if we have a function, that function can be written as the series n from 0 to infinity. Written using Taylor or in Taylor series form as sum from n equals 0 to infinity of the nth derivative of the function f evaluated at some point a over n factorial times x minus a, all raised to the power n. So this is read Taylor series of the function f of x centered at or about a. So this is centered at a. Now, in order to understand the notation, we can let's expand this to find some terms. For example, when n equals 0, we get f, the zeroth derivative of f evaluated at a, divided by 0 factorial plus times x minus a to the power 0 plus f, the first derivative. We don't need to put this in parentheses, we just write the first derivative of the function evaluated at a over 1 factorial times x minus a to the power 1 plus f double prime, that's this n equals 2, of the function f evaluated at a over 2 factorial times x minus a raised to power 2, and so on. Now, what is the zero derivative? Zero derivative, that means we don't have derivative, it's just the function. And what is 0 factorial? 0 factorial is 1. So this is equal to f of a, the function f evaluated at a, plus f prime evaluated at a times x minus a over 1 factorial, but 1 factorial is 1, plus f double prime evaluated at a over 2 factorial times x minus a squared, etc. So this is expansion of the series. As we can see, it's very important to find the derivative. So now, a special case of this series is a special case is when a equals 0, when it's centered at 0, and in this case we call it Maclaurin series. So Maclaurin series is the same as Taylor series evaluated or centered at 0. So we can write it this way: f of x equals the sum from n equals 0 to infinity f, the nth derivative of f evaluated at 0 over n factorial x to the power n. If we want to expand this or find some terms, f of 0 plus f prime evaluated at 0 over 1 factorial times x, because it was x minus a, but a is 0, raised to power 1, x minus a minus 0 is just x, plus f w prime evaluated at 0 over 2 factorial times x squared, and so on. So this is Maclaurin series, a special case of Taylor series. Now let's do some examples. We want to find the Maclaurin series of the function f of x equals e to the x. Now in order to apply this, the Maclaurin series, we need to find some derivatives. So let's find some derivatives here. So let's start with the function. The function is f of x is e to the x. Then the first derivative is the same as e to the x, same function. The second derivative is the same. And just notation here, we can write f double prime of x to denote the second derivative, or f and we put 2 in parentheses of x. If we write this means derivative, but if we write it without parentheses, that means f squared. That's just a notation, and that's why we put the nth derivative here, the n in parentheses, to show that this is derivative, not a power. Now if we find for example, the third derivative of x, it's e to the x, and we usually after 3 derivatives we start putting the numbers into parentheses. For example, for the fourth derivative we don't usually use this notation, but we use this f to the fourth derivative of f evaluated at x. So now we want to find these, to evaluate these functions at 0. So this is e to the 0 equals 1, this is 1, f prime at 0 equals 1, f double prime evaluated at 0 equals 1, f double prime evaluated at 0 equals 1. Now we apply the formula. Here we have f of 0, so f of x e to the x is equal to f of 0 is 1 plus f prime evaluated at 0 is 1 over 1 factorial times x plus f double prime is evaluated at 0 is 1 over 2 factorial times x squared, and so on. X cubed 1 over 3 factorial times x cubed, etc. So this is 1 plus x squared over 2, or 2 factorial, plus x cubed over 3 factorial, etc. And we can write this in the compact form of the series. So we write it as the sum from n equals 0 to infinity, and we can write this as x to the power n over n factorial. If you want to check, just substitute start substituting n equals 0. N equals 0 gives x to the 0 over 0 factorial, but that's equal to 1. That's the first term. When n equals 1, we have x to the power 1 over 1 factorial, which is equal to x. That's the second term, and so on. So we could find Taylor series. We could find a power series expansion of the function e to the x. It's equivalent to the sum from n equals 0 to infinity of x to the power n over n factorial. Now let's back to Taylor series. As we mentioned here, it's a representation of some functions or functions in general using power series. Now if we look at this term or this this expression, this is a number, and this is corresponds to C sub n in the power series because it's a number, but when we apply Taylor series it takes this form, the nth derivative of f evaluated at a over n factorial. So we could find some Maclaurin series. This is Maclaurin series of the function f of x equals e to the x. Now if we want to study the radius, or to find the radius of convergence, so to find the radius of convergence, we need to apply the ratio test. We use ratio test. So ratio test, we take absolute value of a sub n plus 1 over a sub n. That's, we apply this on this power series. So it's x to the power n plus 1 over n plus 1 factorial times the, or divided by a sub n, but we multiply by the reciprocal of this. It's n factorial over x to the power n. And simplifying, we can write this x, or let's write it this way first, x to the power n over x to the power n to make it easier to simplify, and then n factorial over n plus 1 factorial. And this is, now when we cancel x to the power n with x to the power n, and we are left with x to the power 1. So that's x to the power 1 times, now what about this? The denominator here is n plus 1 times n minus 1 up to 1. So we can write it as n plus 1 times n factorial, and then we can cancel n factorial and we get n plus 1 in the denominator. Now after this we can simplify. So we can take, this is the simplest form. Now we take the limit of this, of a sub n plus 1 over a sub n as n goes to infinity, and that's limit of absolute value of x. We don't need to put absolute value for the denominator because this is always positive since n is natural number. N goes to infinity, and that means we have 1 over n. Okay, this is equal to absolute value of x, because the limit depends on n, not on x, times limit 1 over n plus 1, and goes to infinity, but this is equal to 0. So this is equal to 0. 0 is less than 1 for all x values. And that means the radius of convergence is infinity. Now one application of this, of using Maclaurin series or Taylor series in general, is that we can approximate some values. For example, we can use this, use the Maclaurin series to expand or to approximate E. By E, the Euler number e to the power 1. So if we want to find this, actually this is approximately 2.718, so it's with infinite decimal. And if we want to approximate this, we can apply the Maclaurin series. So we have e to the power 1, so x is equal to 1. We know that e to the x equals the sum x to the power n over n factorial n from 0 to infinity. And now e to the power 1 is the sum n equals 0 to infinity x to the power 1 over 1 factorial, and that is, okay, so over n factorial. Actually x equals 1. It's 1 to the power n, which is the sum 1 over n factorial, n from 0 to infinity. And that's, now we substitute, for example, n equals 0 to get 1, because 0 factorial is 1, plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, etc. And this is an approximation of E. So E can be approximated by this 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, If you evaluate some value or find the sum of this infinite series, you get the value of E. So this is one application of finding Maclaurin series, or in general Taylor series. Now let's do, before we continue in the examples, let's talk about partial sum of Taylor series. What is partial sum? Partial sum of Maclaurin, of Taylor series in general. Taylor series. Now, partial sum of Taylor series So partial sum of Taylor series, for example, we know that f of x is the sum from n equals 0 to infinity, the nth derivative of f evaluated at a over n factorial times x minus a to the power n. Now to find the partial sum is t denoted as t sub n of x, and we are interested in finding just n terms of the sum of n terms of this series. So we have sum, let's use the notation, the simple I from 0 to n, not to infinity. So we are interested in n terms. So this is f, the ith derivative of f evaluated at a over I factorial times x minus a to the power n. And now if we want to expand this, we get f of x, or f of x evaluated at a, that means f of a when I equals 0. And then f of prime evaluated at a over 1 factorial times x minus a plus f double prime evaluated at a over 2 factorial times x minus a squared plus up to f, the nth derivative of f evaluated at a over n factorial times x minus a to the power n. So this is the nth or the partial sum of Taylor series. This is called, now Tn is called, this is called the nth degree Taylor polynomial, because if we simplify this, we get a polynomial actually here. So this is a polynomial of f of x at a, or evaluated at a, or centered at a. Now Maclaurin series, for example, Maclaurin series for e to x, f of x equals e to the x, if we want to find the nth degree Maclaurin polynomial, we can find it this way. So by considering Maclaurin series, we can find Maclaurin polynomial, or Taylor polynomial, nth degree polynomial by applying the sum from n equals 0 to n, or from I to equals 0 to n of f, the ith derivative of f evaluated at 0, because a is 0 in Maclaurin, over I factorial times x to the power I. So this is in general. This is equal to the sum from I equals 0 to n x to the power I over I factorial, because this is always equal to 1 for e to the x. So we get 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial up to x to the power n over n factorial. Now if we are interested in finding some of these polynomials, let's find the first polynomial, t sub 1 of x, the Taylor polynomial. This is the sum from n equals 0 to n equals 1 of x to the power n over n factorial. Now substitute n equals 0, you get 0 x to this 0 over 0 factorial, and then substitute n equals 1, you get x to the power 1 over 1 factorial, and this is equal to x to the power 0 is 1 over 0 factorial is just 1 plus x. So this is the first Taylor polynomial. The second Taylor polynomial is the sum from n equals 0 to 2 of x to the power n over n factorial. Now this is, now we substitute x0 or n0, x to the power 0 over 0 factorial plus x to the power 1 over 1 factorial plus x to the power 2 over 2 factorial, and that is 1 plus x squared over 2. Now if we want to find the third Taylor polynomial, that's the sum from n equals 0 to 3 of x to the power n over n factorial, and that's x to the power 0 over 0 factorial plus x to the power 1 over 1 factorial plus x to the power 2 over 2 factorial plus x to the power 3 over 3 factorial, and this is 1 plus x squared over 2 plus x cubed over 3, or sorry, 3 factorial, and that's 6. Okay, now these are polynomials. As we can see, these are polynomials, because a polynomial is a function that can be written in this form, and the power of x, of each x or each variable, is non-negative integer, as we can see in these examples. So these are some Taylor polynomials. And now let's graph these polynomials. For some reason I want to graph these polynomials. So if we want to, let's first graph the original function. The original function is e to the x. So f of x is e to the x. Now the graph of e to the x looks like this. This is the graph of e to the x. It intersects the y-axis at 1. So this is e to the x. This is the exact function. Now if we graph t1, t1 is 1 plus x. When we graph this, we get graph like this. The x-intercept is -1, and it intersects at the y-axis, or the y-intercept is 1 as well. So this is the t1. Now let's graph t2. t2 is this function. If we graph this function, we get a graph like this one. This is t2. If we graph t3, t3 is cube function or cubic function. The graph looks like this. And as we can see here, we get a better approximation of the function. We get a better approximation of the function, as this is t3. So notice here that x3 is very close to the graph, because the graph of the e to the x, the original function, looks like this, and t3 looks like this. So this is very close, or it's, let's say it's close. And as n get increased, as n increases, t sub n of x, the nth polynomial, goes to e to the x, that means it becomes almost, t sub n of x can be a good approximation of e to the x. And as n goes to infinity, t sub n of x is equal to e to the x. And we write it this way: limit as n goes to infinity of the nth polynomial is e to the x, the exact value. And that means these polynomials, these Taylor polynomials, can be used to approximate the function, approximate some functions. Sometimes we can't find integration, so instead of studying integration, we study the expansion, Taylor expansion, and then integrate that expansion to get an approximation of the given function. Okay, now, but as we can see, these are just approximations. That means we still have some difference between the exact and the approximation. We still have that difference. So that difference is the remainder. So we define r sub n of x, this is the remainder of the Taylor series, is defined as the difference between the exact value of the function, or the exact function f of x, minus the nth polynomial, the Taylor polynomial. This difference between the exact and the approximation is called the remainder. So this is called the remainder of the Taylor series. And here the remainder has the following property: limit of the remainder as n goes to infinity. When we get, as we've seen here, as n goes to infinity, this difference between the exact and approximation becomes almost zero. So as n goes to infinity, this remainder, the difference between the exact and the approximation, will be zero. So that means, this means that limit of Tn as n goes to infinity, the approximation will be exactly equal to the exact function. Now here, in working with this, in order to show that the difference or the remainder of the Taylor series is equal to zero, we usually use the following useful inequality. The inequality is called Taylor's inequality. And this inequality says that if the absolute value of the n plus 1th derivative of x, of the function f of x, is less than or equal to some constant m, call it m, for absolute value of x minus a less than or equal to some value, some constant, then the absolute value of the remainder is less than or equal to m over n plus 1 factorial, all multiplied by x minus a to the power n plus 1 for same interval of convergence, x minus a, absolute value of this less than or equal to d. Now, how to use this? For example, we can use this with our function f of x equals e to the x. We want to show that e to the x is equal to the sum of Maclaurin series. Now, to show this, we need to show this first. The n plus 1 derivative of the function, absolute value of that, is less than or equal to some constant m. Now, how to show this? We find the n plus 1 derivative of the function, but we know that this is nothing but the original function e to the x, because any derivative of e to the x gives e to the x. Okay, so absolute value of x, we need to find a bound for this. Now this is less than or equal what? Now we know that for Maclaurin, we know that x, the absolute value of x minus a, is less than or equal to d here from Taylor. But for Maclaurin, a is equal to 0 since this is Maclaurin. So we have x, absolute value of x less than or equal to d. Now we take e as a base of this inequality. We get e to the absolute value of x less than or equal to e to the d. And this is a constant. We can call this constant m. Now we apply it here. So, or we apply it here in this formula. It's our inequality. So we have absolute value of r sub n of x of the remainder is less than or equal to m. M is e to d, and that's equal to m, over n plus 1 factorial times x to the power n plus 1, because a is equal to 0 for Maclaurin. So this function is bounded, and we find that the limit of this, now this is for absolute value of x less than or equal to d. Now take limit of this, limit as n goes to infinity. This is equal to, now limit of both sides. We get limit of absolute value Rn of x less than or equal to limit e to the d, which is m actually, over n plus 1 factorial times absolute value, I should put absolute value here, of x to the power n plus 1. And as n goes to infinity, and this is, since e to the d is just constant, we put it here in front of the limit, n goes to infinity, of absolute value of x to the power n plus 1 over n plus 1 factorial. Now since the denominator involves n and the power in the numerator we have x raised to some power, this is equal to 0. So we have that e to the x is the sum. We've seen that the remainder is equal to 0. So the remainder is, limit of the remainder is 0, and that means this is exact value. This means e to the x is equal to the sum of Maclaurin series. Now let's take some examples of Maclaurin series. Let's start with the following example. We want to find the Maclaurin series for f of x equals sine of x. Now for this function we need to find some derivatives, because we know that the Maclaurin series is the sum of f, the nth derivative of f evaluated as 0 over n factorial times x minus 0 to the power n, which is just x to the power n from 0 to infinity. Now we find, so this is f of x, and then we find the some derivatives to generalize f, or to find the nth derivative, the formula for the nth derivative. We find that f of x is sine of x, f prime of x is cosine of x, f double prime of x is negative sine of x, and f to the power, the third derivative of f is equal to negative cosine x. The fourth derivative of f is sine of x. And then we evaluate this at 0. F of 0 is sine of 0 is 0. Evaluate this at 0, you get 1. Evaluate this at 0, you get 0. Evaluate this as 0, you get -1. Evaluate this as 0, you get 0. So when we expand this, we get f of 0 plus f prime of 0 over 1 factorial times x plus f double prime of 0 over 2 factorial times x squared, and so on. So we have here f of 0 is 0, f of 1 is f prime of 0 is 1 times x plus f double prime gives 0 times x squared plus f triple prime is -1 over 3x cubed, and the f for the fourth derivative times evaluated at 0 times x to the fourth, and so on. So we get x minus x cubed over 3 plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so on. And we can write this using the compact form of the series form using sigma notation. So this is sum from n0 to infinity. Now we have the sign is alternating here, so we can write -1 to the power n, since n starts from 0, to get +1, -1, +1, -1, and so on. And x, since the power is 1, then 3, then 5, then 7, we know that the general form for this is 2n plus 1. For example, substitute n equals 0, you get 2 times 0 plus 1 is 1. Substitute n equals 1, you get 2 times 1 plus 1 is 3, and so on. Over 2n plus 1 factorial, that's the denominator. Now this is 3 factorial. Okay, so this is Maclaurin series. The Maclaurin series of the function sine of x is this. This is Maclaurin series. Now if we want to show that the remainder is 0, to show that limit of Rn of x as n goes to infinity is equal to 0, then you need to find the nth derivative. As you can see, the n plus 1 derivative of x is either the derivative of the function is either cosine or sine with plus or minus sign. So this is either plus or minus sine of x or plus or minus cosine of x, and that means the absolute value of this derivative is, we know that sine and cosine can have values between from -1 to 1, cannot exceed 1. So absolute value of this is always less than or equal to 1, and this is m. So we have r sub n of x is less than or equal to m over n plus 1 factorial times x minus 0 to the power n plus 1 using the inequality shown before, for x minus 0 less than or equal to d. And this is less than or equal to m is equal to 1 over n plus 1 factorial times x to the power n plus 1 for absolute value x less than or equal to d. Now take limit n goes to infinity of Rn of x. This is equal to 0 because the limit of this is equal to 0. This is goes to 0 as n goes to infinity. Now let's take some other examples. For example, if we want to find Maclaurin series for f of x equals cosine x, same thing here. We can write f of x as, using Maclaurin series, sum the nth derivative evaluated as 0 over n factorial x to the power n, and from 0 to infinity. We need to find some derivatives. Actually, this is can be written as f of 0 plus f prime evaluated as 0 over 1 factorial x plus f double prime evaluated as 0 over 2 times x squared, f triple prime evaluated as 0 over 3 factorial times x cubed, and so on. Now we can find f of 0. This is f of x. So let's find some values. F of 0 is cosine of 0 is equal to 1. F of prime of 0, f of prime of x is negative sine. So f of prime of 0 is negative sine of 0, and that's 0. F w prime evaluated as 0, negative sine, derivative of negative sine is negative cosine, evaluated as 0 is negative 1. And then f triple prime evaluated as 0, derivative of negative cosine is sine, evaluated as 0, this is 0. The fourth derivative evaluated as 0, derivative of sine is cosine, evaluated as 0 gives 1. So we can substitute these values here to get 1 plus 0 plus minus x squared over 2 factorial plus 0 minus etc. And that should give us this form: 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. And we can write this using the sigma notation, sum from 0 and equals 0 to infinity. Now this is alternating, positive 1, negative 1, positive, negative, so negative 1 to the power n, x to the power, now this is even power, so we should write it as 2n. When n equals 0, we disappear, x disappear. If n equals 1, we get 2, n equals 2, we get 4, n equals 3, we get 6, and so on, over 2n factorial. So we could write the Maclaurin series of this function, the cosine function. Now, sometimes we are interested in finding the Maclaurin series of the multiplication of two functions or division of two of these functions. For example, how to find Maclaurin series for the function f of x equals x cosine x. Now let me remind you of some basic Maclaurin series that we already found. So let's start with the important Maclaurin series, or important results for Maclaurin series. 1 over 1 minus x can be written as the sum x to the power n, and from 0 to infinity. We learned this from a previous lecture. And here radius of convergence is 1. This can be found directly from power series formula. We don't need to apply a Taylor series to find it. Now we need to remember sine of x. We already computed here in this lecture is the sum from n equals 0 to infinity, negative 1 to the power n, x to the power 2n plus 1, because it's odd, we write it, the power is odd, can be written as 2n plus 1 over 2n plus 1 factorial, and here r is infinity, the radius of convergence is infinity, and 3 cosine x we just computed, so it's sum from n equals 0 to infinity, negative 1 to the power n x to the power 2n over 2n factorial, and here r is infinity, radius of convergence is infinity. So we should remember these three results in order to use them to find the Maclaurin series for more complicated functions. So let's apply it here. So let's find the expansion for f of x, or the Maclaurin series for f of x equals x cosine x. Now for x cosine x, we just multiply, we have x times, what is the Maclaurin series for cosine? For cosine, it's the sum from n equals 0 to infinity, negative 1 to the power n x to the power 2n over 2n factorial. Now we multiply x by x, we multiply this by this to get the sum from n equals 0 to infinity, -1 to the power n, x to the power 2n plus 1 over 2n factorial. Now we can find a power series of, let's take another example. Let's find it for, find the Maclaurin series for the function f of x equals x e to -2x. Now for this function we use the basic functions, the basic results here. So we have x times e to the -2x. What is e to the x? Actually, I should add e to the x here to this list of results. E to the x, we computed this in this lecture, is x to the power n over n factorial. E to the x is the sum from n equals 0 to infinity, x to the power n over n factorial. But instead of x, we have -2x. So we just substitute -2x. So this is sum from n0 to infinity, -2x to the power n over n factorial. And now -1 to the power n is -1 to the power n. We just distribute the power times 2 to the power n times x to the power n over n factorial. And now we need to multiply by x. So we have the sum n equals 0 to infinity, -1 to the power n, 2 to the power n, x to the power n plus 1 over n factorial. And sometimes we prefer to write the power of x as n, not n plus 1. So if we can simplify it to n, that's better. So how to do that? In order to do that, we just replace n with n minus 1. So we replace n with n minus 1 here inside the series, and we need to shift the index from n equals 0 to n equals 1. So we reduce this n and add to the n here. So if we subtract 1 from n inside the series, we add 1 to the index. So we have the sum from n equals 1 to infinity. Now we need to replace each n with n minus 1, 2 to n minus 1, x to, now n minus 1 plus 1 is just n over n minus 1 factorial. So we could write it as x to the power n, and that's preferred form. Now this is convergent for all x, since the original Maclaurin series is convergent for all x. So if we have, for example, if we want to find the first 3 non-zero terms of Maclaurin series for first e to the x sine x, let's find this first and then we apply the division. So this is, what is e to the x? The expansion of e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial times, what is the expansion of sine? Sine is x minus x cubed over 3 factorial plus x to the 5 factorial minus And then when we multiply them, we need to multiply them this way. So we have the first series here, 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and then here we write this expansion. We have x minus x cubed over 3 factorial. We can continue, but let's just use those because we are interested in finding just 3 non-zero terms. Let's multiply. X times 1 is x, x times x is x squared, x times x squared over 2 is x cubed over 2 factorial, which is just 2. X times x cubed is x to the 4th over 3 factorial, which is 6, etc. Now we multiply this by, we distribute this, we multiply it by 1, we get negative x cubed over 6, 3 factorial, minus x to the 5th, because to the 4th, over 6, minus x to the 5th over 12, and so on. And then we add. When we add, we get x plus x squared plus, now we need to add these together. When we add these together, we get x squared over 2 plus, when we add these, we get x to the 4th over 6, etc. But we are interested in finding the first 3 terms. Those are the first 3 terms. Now for the second example, we apply the division. So we want to find expansion or tail of Maclaurin series for the first 3 terms of Maclaurin series for tan of x. For tan of x, we need to rewrite it in terms of the basic functions. So tan of x is sine of x over cosine x. But sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus etc. Over what is cosine? The expansion for cosine is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus etc. Even powers. And then we need to divide those two polynomials. So we use the long division. The numerator is x minus x cubed over 3 factorial, which is 6, plus x to the 5th over 5 factorial, which is 120 minus etc. And we divide by this, by 1 minus x squared over 2 plus x to the 4th over 24 minus etc. Now when we divide the first term by the first term. X divided by 1 is x, and then we distribute this on these terms. So x times 1 is x, x times negative x squared is negative x cubed over 2, x times x to the 4th is x to the 4th over 24, etc. Now we change the signs, so this becomes negative, this is positive, this is negative, and we simplify. When we simplify, we get x cubed over 3 minus 1 over 30 x to the 5th. This is x to the 5th. So you just add the subtract here. Now we do same process. We divide this by the first element. So this is x cubed over 3. And when we distribute it again, we get x cubed over 3 minus 1/6 x to the 5th. And then we change the signs. Change this sign, and we get 2 over 15. We have 2 over 15 x to the 5th minus 1 over 30 x to the 4th, and then we divide again by the first element, we get 2 over 15x to the fifth, and then we distribute it again to get 2 over 15x to the fifth minus 1 over 15x to the seventh. We change the signs. This becomes negative, this becomes positive, and that's it. Actually, we don't need to simplify more because we already obtained the first three terms.